It's only been 2.5 years. We all know how to video conference. We'll just re-record that. Okay, so what it means is we only guarantee logical security claims relating to implementation or physical security, implementation correctness or physical security. We rely on the same set of certifications that any secure element vendor would be familiar with. Not going to talk about that in here. I'm going to try and keep it to the interesting stuff, but I'm happy to talk about that with anyone afterwards. So by analogy, the Linux kernel does not make a full operating system. You have to wrap a lot of additional stuff around it. Similarly, we provide a core open source project, and then you need to add a lot of additional proprietary stuff that we kind of call out here on the right in order to make that into an actual saleable chip. So we do, besides the project, have this concrete notion of a silicon product that has all the necessary analog bits, clock, physical countermeasures, everything that's absolutely necessary in order to create a real design. And this works because this project is something that we're coordinating closely with our backend partners and project members, Nuvoton, to actually create this first discrete silicon device, this root of trust chip. And we're gonna have the first one, our first engineering samples next year. I'm gonna be vague on timelines because I don't want anyone to hold me to them. So today we have silicon software and security working groups, and they are really focused on this design. If you want a real close analogy, you can think about it as basically equivalent to a TPM, but without the prescriptive API. And we've actually also just chartered and begun work on our integrated, as in like large scale SoC root of trust family of designs. We're going to be expanding into something we call multi-top, which is this notion of having multiple, although finite number of trademark compliant designs that are really just suitable for, plopping into a larger design or hitting different price or performance points while still providing the same set of foundational security guarantees that we care about. And then fundamentally, we believe that if something can be open source in this domain, we will make it open source, but we do have to actually produce a chip. And so not everything can be open source. Fix one thing, broke another. There we go. Okay, so just as an aside, I want to be really clear about this, that when we say open, we mean open. That second link is a GitHub link. It is open today in both implementation and process, not eventually, not when we get around to it, not when it's quote unquote done or finished. It never is. It's a reality right now. It's also not an open standard. It's an open implementation because standards are not standard when they get implemented. And it's really important to get this right. And it's also not developed in some kind of a proprietary method and then kicked over the wall without support or without, say, design verification. It is a complete silicon design, down to the boot ROM, reference OS, all of the infrastructure that goes into actively maintaining something like this. So this isn't open washing. It's open as far as we can go. Today, where we are after 4.5 years of work, 2 of them fairly quiet, and this all includes the IBEX core, this RISC-V 32-bit core that is also supported by OpenTitan. We've got this nice kind of linear graph, right? But that's not really enough. This doesn't really speak to the success of the ecosystem. This is something that this is all hosted by the Low Risk Community Interest Corporation, this independent nonprofit. So they're responsible for maintaining all this other stuff that's more than just the commits, which I'm going to go into later. But we call that kind of set of all the collateral that enables our collaborative engineering process the Silicon Commons. It's this notion of having an open, well-supported collaborative space. So really, open source development is more about community. It's about maintaining other people's code and them in turn maintaining your code for you. So let's talk about what a healthy community looks like. It is a lot of diverse skills, diverse partners, working towards common goals. So these partners all actually support the low risk organization, both in an engineering sense, but also financially, because open source is not free. It's not free to develop. It's not free to use. It is, it takes quite a bit of effort, actually. So this partner coalition, they really rely on having this Silicon Commons maintained by an independent third party to keep the code base green, to do regression triage, to coordinate the various working groups, to make sure that everything is held to a high consistent standard, one that is suitable and credible for a commercial tape out. So all in all these partners together provide us the rich, diverse set of talent necessary to successfully build a Silicon root of trust in the open source. It's not just the partners. The page full of logos is always nice when you're talking about fundraising, because everyone wants to be part of the club, but a healthy open source project also has significant ongoing engagement from people actually doing the work. So this is a graph conveniently provided by GitHub over a month period that really demonstrates that this is a live, active, dynamic project. We sometimes think about open source projects when they're kind of up and going and successful as being an open source flywheel, something where you kind of hit a critical mass and it sort of takes itself forward based on whatever structure you put in place. So for us, it's really not just about creating these common silicon designs and collateral. It's actually about creating and maintaining the shared environment that supports this collaborative development. That is where a significant amount of our time and communication go towards. And it's not just code, right? It's the comments on, the comments on the pull request. It's the handling of issues. It's the making sure everything is categorized, making sure we're burning down towards specific milestones that have to do with getting the tape out, and just kind of keeping that going over a long period of time. Excuse me. So there also has to be some structure. You have to have some coordination to keep things moving forward in a consistent fashion. The way we feel like we've gotten this right is when we bring folks who have open source software experience onto the project. They say, this is nuts. You guys are way too controlling. It's way too structured. Like, I just want to hack. And then when we bring proprietary or kind of silicon folks who have deep experience in their domain onto the project, they say, well, this is chaos. You're never going to be able to produce a chip. So everyone is fairly equally uncomfortable. So we've kind of struck a balance between kind of giving folks the freedom to contribute where they want to, where they're able to, but also making sure that those contributions are building towards something larger that is coordinated, because a real silicon design is quite large. It requires tens of people, sometimes over multiple years, usually over multiple years. And we built everything from scratch, right? Because this is an open source design, we don't have a proprietary core in there. We don't use proprietary DVIP. It is all from scratch. So how do we create this alignment in a way that's palatable to all parties? We borrow extensively from open source software development practices, constrained by the requirements of producing silicon. We also start with a vanilla Apache license because we don't really want to spend more time with lawyers than is necessary, although I do spend quite a bit of time with lawyers regardless. There is a project director, which is myself, who's responsible for setting the overall direction, proposing the yearly roadmap, which is voted on by the technical committee, the steering committee. That steering committee is composed of the people who are contributing financially to the project because they should have a say in the direction of the project. They provide feedback on the roadmap, approve or reject it. They also are responsible for evaluating new technical committee members, who are typically composed of people very engaged, technical individuals, very engaged in the day-to-day operation of the project. So they provide direct feedback on what actually defines something that's OpenTitan TM. They're also responsible, the technical committee, for approving new committers. It is a reasonably high bar, not just anyone can be a committer. So we do take that quite seriously. And then finally, there are the people who are really making it happen, who are doing all the work. And these all tend to overlap with the previously mentioned roles, myself excluded. I mostly send emails these days. But there are a fair number of people who are really doing the engineering input necessary to make this happen. And those are the contributors. And we owe the success of this project to them and their dedication. All right, for the next section, I'm going to talk quickly about our technology and kind of three different views. First, architecturally, kind of a top level view, as well as some key aspects of the security architecture. Then diving in deeper on a few of the individual blocks, especially focused on key logical operations of identity and ownership transfer. That is identity, comma, and ownership transfer. And then finally, a peek at the system level, our generic countermeasures, how we handle security kind of at the very top level of the chip. This is by necessity going to be a relatively incomplete view of the design, but as the project is very large, not enough time to cover everything. It's all documented on the web. You can see, a lot of these slides were actually pulled directly from there. I do apologize for the organization. We are getting to it, but it is all there, and it's all there right now. So this is the top level of the chip. This is the primary discrete design that we are all working on today. It's a root of trust. It looks like a lot of other roots of trust. It looks like a secure element. It looks like a TPM. If you squint, these things all kind of belong in a family of devices. You see the same IP blocks popping up over and over and over again. Really, it's possibly better to think of this as just one instance of a secure microcontroller kind of built from this family of highly compatible IP that we have developed. It's called Earl Grey. That's the name for this particular top level, which is the chip itself. And it has all of the things listed there. Going in a bit deeper, so I am going to vastly oversimplify what a root of trust does and state that it has to do two things. One is attest to the authenticity of the silicon, and two, to be able to attest to the authenticity of the firmware running on that silicon. And both of these things are rooted in identity. Doing those two things well is quite difficult, requires a lot of work. But a lot of, if you kind of squint, that really is what it has to do. And then you can build a lot of trust on top of that. So if folks are familiar, we do try to be as compliant to well-accepted standards as possible. So our identity scheme is compliant with something called the DICE open profile, which is slightly different than DICE. It is, I'd say, a superset of DICE. So it is both compliant with DICE and the DICE open profile. We also have a distinct notion of the device creator and the device owner identities. And those are both really meant to be typically coalitions. More often, the owner would be a single entity, but the creator is definitely meant to be a coalition. The top two blocks of the identity derivation scheme are basically creator identity derivations, and they must be and are implemented as open source. This goes to our trust model, not our security model nor our threat model, but our trust model. Those must be open source. It is a non-negotiable point. Below that or above that, depending on which direction you're coming from, the owner can choose to either have an open or proprietary payload. It's an ownership transfer mechanism that I'll touch on that really enables that. The identity root secrets and the internal key manager state, that's all hidden from software, including the ROM, that all happens off on the side, really allowing us to simplify the software hardening. And then the key manager, which I'll touch on again later, supports two primary key derivation chains. One is this DICE compliant chain, and then the other is a sealing chain, which we can use to implement a more stable key derivation scheme. So ownership transfer, and I appear to have clipped the title off of this, but this is the ownership transfer slide. This is the means by which an owner, again, this is a logical entity, can take possession of the silicon. So no one really, in my view, or certainly in the domain I work in, wants to have to ask permission to run code on hardware that they have purchased. You paid money for it, you own it, you should be able to run code on it. So we don't do dual signing or anything like that. You don't have to go to the SoC vendor and ask them to sign your payload that you've already, we don't do that, right? It's a in-field ownership transfer mechanism. So in practice, this is a two-part trust model. Like I mentioned, every measurement of an immutable component that can all be constructed out of band. So basically everything that is fixed at manufacturing time is open source by necessity. And then all of the mutable components like the flash can actually be mutated via the ownership transfer. So you can, in a sense, switch PKIs in post-manufacturing. So this is pretty important, right? This is kind of one of the things we think is really useful about this design. It allows us to do kind of a lot of late binding integrations or payload integrations. And it also is something that makes the design much more palatable to a number of our partners, to a number of the corporations that we do work with and who are going to end up buying these things at the end of the day. It also fundamentally respects the user of the device more. So there are 3 steps in an ownership transfer, and I apologize that that text is so small, but oops. If you're going to do an ownership transfer operation, a new owner would verify that the device is authentic by checking the device attestation, the creator certificate. Then the new owner would take ownership of the device by loading code signing verification keys and signed software, boot into the new owner signed code, and then the owner can attest that the new hardware and software configuration and use that to verify the integrity of the device. And then they can inject or generate their own secrets or application-specific secrets. So that would be like an in-field owner provisioning operation. And then once the owner is ready to relinquish ownership of the device, they clear secrets, and then they transition that device into a state in which it can be disposed of or assigned to the next owner. So this would be like a device unlock state. Not necessary to endorse the next owner keys. A creator or manufacturer can actually opt to leave the device in an unlocked state. This is our strong preference, so that anyone can execute that initial ownership transfer without a signed payload. Right now, a lot of this relies on having a discrete design with embedded flash. We've got a couple of different architectures to support this for the integrated root of trust as well. But this notion of ownership transfer, while it makes certification more interesting, is really important for this project to be able to support. So again, this ownership transfer mechanism guarantees that the chip works for the person who owns the chip. All right, so identity and ownership transfer, we consider those crucial features. They're pretty important. Their implementation is at the heart of our trust and security model. So talking a little bit about the hardware and software that implements that. Lifecycle controller. So new device identities, not owner, but device identities or creator identities can only be minted at manufacturing, and that pathway is irrevocably closed after it is used once. So this is kind of, it touches on, it touches every individual design, digital block, IP block that has different configuration settings based on the life cycle of the device, right? So if you go into ARM-A, you can't then go and read secrets out. So really, really important functionality for both provisioning the device at the manufacturer or the OSAT, wherever it is, but also in terms of, building debug versions of the devices or production versions of the devices. Lifecycle controller touches everything. And then there's the key manager, which isolates all of the key state from the main processor. Key manager generates keys for software consumption, but for certain blocks, AES, KMAC, and what we call OTBN, OpenTitan Big Num Engine, big multiplier. It has side load capabilities, so we can keep that key material from going through the main processor pathway. These all have countermeasures, which I believe are all upstreamed at this point. States, critical control signals, DFT, JTAG, things like that. They get redundantly encoded to help deal with fault injection. FSMs are sparsely encoded to help deal with control flow integrity. And for instance, the RMA has a difficult to brute force test unlock. There are just a number of countermeasures scattered throughout these designs because that's what's necessary to get something in the open source certified. You got to kind of overbuild it. A couple of other blocks that are, of interest, KMAC in particular, the AES is the AES. We do implement first order domain oriented masking, and we did some formal verification work on AES and I believe KMAC using Rebecca. And then we also have a set of what we call primitive countermeasures. And these are countermeasures that often have a very stylized form of verification attached to them that we sprinkle throughout the design, say like multi-bit encodings on signals, things like that. It's not up here, but again, it's on the website, but I do want to mention it is this Big Num Engine, our wide multiplier, again, primarily developed by Low Risk. Very cool little machine, 32-bit instruction path, heavily influenced by RISC-V, and a 256-bit data path. One of the most interesting things about this is that we actually worked with Brian Parno's group at CMU to formally verify our ModEx for RSA with Daphne and Veil. So that is formally verified code using those formal verification frameworks that we are actually preferentially going to be executing in production. We also have a software implementation because we don't want a dead chip, but for the stuff that we expect to be using most of the time for a speedy boot, that is actually formally verified, or at least the core routines are formally verified. So moving on to kind of the system level technical features, I'm also going to touch on how our primary core is integrated. We have, like I said, these generic countermeasures, the sparse FSMs, redundant counters, LFSRs, all that kind of stuff, where we have a very specialized DV methodology, so we can rapidly add those to whatever FSM or signals that's useful for, and not have to go and redo all the design verification, because at the end of the day, design verification is always the long pole. So anything that we can do to kind of abstract that or leverage work that we've done previously, we absolutely do. And then, of course, we have all these other, miscellaneous countermeasures that we use to get the design ready for actual tape out and evaluation in a lab setting. So really quickly on IBEX, while we do isolate a lot of the secrets and critical assets away from the processor cores in our case, it wouldn't be a very useful device without a microcontroller core and a boot ROM. So we use IBEX. If you're familiar with RISC-V, 32-bit IMCB, where the B is, I believe, a subset of the bit manip instructions. This used to be ETH Zurich's Zero Risky core from Luca Bonini's lab, but it is now hosted, developed, maintained by Low Risk as a component IP. But again, it's best to think of this as one component in a larger ecosystem of high quality open source silicon design IP. One interesting thing about this is we actually implement it as a dual lockstep configuration to prevent it, to help address fault injection attacks. The boot ROM, as I mentioned, primarily we expect to use OTBN's implementation. We do have a software implementation because, again, we cannot have dead silicon coming off the line, and if you can't make it past your verified boot, then you're hosed. We only support RSA 3K and only 65537 for the exponent. We, I believe, had like we had one of the small ones, or we had the small one as well. We evaluated it. It turned out we didn't get much of a speed advantage because of the acceleration. So we just went with the one that is easy to get through FIPS. Because having gone through FIPS a couple of times, I will take any shortcut there that I can. So system level security, it's important to realize when you build one of these secure devices, it's more than just the individual cryptography blocks, it's the whole system. So we have an alert handler responsible for aggregating and responding in a programmatic fashion to these out-of-band hardware alerts. Many of the cryptographic blocks have hardware alert lines. Obviously all the sensors have hardware alert lines. We do have physical sensors in there. Those are by necessity not open source, but we do have this scattershot kind of analog set of light and glitch and clock drift and all the kind of standard stuff that you would put in one of these devices. Then we also protect the kind of system bus and the various memories with SHA encoding and the appropriate, I don't want to call them ciphers, but scrambling primitives as well. And it's worth pointing out, if people have questions about this stuff, a lot of the folks who are responsible for it are actually here today. You'll see them by their lovely royal purple hoodies with our awesome Open Silicon logo on it. So feel free to ask them and they'll either tell you themselves because they probably committed quite a bit of this code, or they will direct you to the right person. So quickly, some of the challenges and our solutions to those challenges. Open Silicon, to the best of my knowledge, has not been done at this scale before. It has certainly been done before. I have spent many an evening lamenting the quality of things on, I can't remember the name of the site now. But there are some real challenges in doing this and doing it at scale. So the technology, the IP we develop, that's important, but it's only one component. So kind of two facts in opposition. The first is that we have a highly distributed team, physically, organizationally, culturally, in a traditionally proprietary space, silicon, and then again, working in a specialized domain, silicon security. Second fact is that commercial silicon is usually the result of a pretty cohesive team that's highly coordinated, a very resource intensive effort over a long period of time. So we have to take those two very difficult facts and fit them together such that we're able to effectively coordinate across vast distances of all kinds on this unified design. And you don't do that by accident. It takes a lot of intent and effort. It's taken us 4.5 years to get to where we are today, but where we are today is in a pretty good spot. So our solution, maybe the solution, is to create this Silicon Commons that is maintained by a third party that really works for the benefit of all of the participants and in an active way. This is not a passive project. So this Silicon Commons is really the difference between a kind of scare quotes open source project, like throw it over the wall, and this OpenTitan effort, which is an actively maintained ecosystem of inherently compatible security focused, but not just security silicon, open source silicon IP. So it's kind of composed of a set of policies, technologies, and processes to support collaborative engineering across all these different groups. But there's also a very large educational component that helps bring people along who might not have open source experience or might not have silicon experience and understand why your DB team is so angry at you all the time. So there's a lot of kind of bringing people to the same level so that we're all speaking the same language. Again, open source isn't free. It requires funding, participation, and a strong ethos of collaboration to keep something maintained and relevant, especially in the long term. And the reason why open source is valuable, one of the reasons why open source is valuable, it's almost never because it displaces something that you're paying too much money for. Typically, the things that are kind of open source amenable are already being commoditized, and it's just kind of reaching a logical conclusion. So what it really is, the value it has is in creating a common commoditized artifact that addresses the needs of all of these parties who are investing together without putting the burden unduly on any one of them. So this is the structure that we've built these last 4 years. So the goal has been to prevent the engineering commons from becoming a tragedy by providing this kind of framework for everyone to work well together. An example, let's take a policy or contribution workflow. This is very strict. We have had people come and say, well, I am not going to respond to your approver's comments on my PR. And we say, well, they are the approver and it doesn't really work that way. So, our hands are kind of tied. Not just anyone can commit code and not just any one person can commit code. We have a two-party rule because that's a good rule and it increases the visibility on anything that's committed. The bar to become a committer is quite high. This is a perennial topic of discussion within the TC. We don't have fixed metrics, but we do kind of have a lot of insight into what people are contributing to the project. So we can make pretty good judgments about, who should get commit rights and who shouldn't. And it's almost never the case where we say, oh, no, that person shouldn't get commit rights. We say, well, we'd really like to see more contributions in this domain because they're definitely on the right path. We do actively prune that committer list. It does not just grow upwards monotonically. We make sure that it's active people who are actively working on the project so that we don't just have additional privileges floating around there willy-nilly. So you would think that this kind of process is familiar to most people. It turns out it's really uncommon in the Silicon world for things to work this way. And that's for very reasonable reasons. Different incentive structures lead to different design methodologies. But it's important that we get everyone working on the same design methodology. So for us, one of the things that's really, really paramount is a high quality design, because that provides a lot of value, which incentivizes adoption. And so we don't measure our success by necessarily the first chip or the second chip. We measure it by what is the uptake, right? What is the influence that we are able to have on other designs going forward? And it's also worth mentioning, we do have escalation processes in case things get wedged, because you get two kind of failure modes in these open source projects. One is people putting stuff in there that they shouldn't, which this process prevents, and one is people sort of preventing progress from happening, which the escalation process helps prevent. And the escalation process is usually to email down. So what about the technology component? Continuous integration. This is a really good example of the kind of infrastructure that we've had to develop over the last 4 years. This infrastructure, we're making some cloud company a reasonable amount of money as our design scales up and we have to run more and more integrations. It's really important to test changes. It's really important to keep the code base as green as possible, as much as possible. And so this is a way for us to get automated feedback, which the committer is then responsible for addressing before we can actually will allow a merge. Another big goal of the CI workflow is we want to, not the CI, but our workflow in general is to have small contained changes being merged often. Incremental change is much, much easier to handle, review, integrate into the project than someone chunking in a 5,000 line design. Those basically get rejected out of hand because it just doesn't work. We have definitely learned it just doesn't work. So OpenTitan moves quickly, so quickly that things break. It's just normal, it's natural. So what we've done, one of the things we've done on the process side is we have established a weekly rotating 2-person on-call team. So this is typically a digital designer and a design verification engineer who are responsible for issue triage. They don't have to solve everything themselves. What they do have to do is, commit up to 80% of that time, that week that they are on call, to handling issue triage, solving issues themselves if possible. And when I say issue, I mean like literally like GitHub issues, like an artifact. So the other thing that the on-callers can do, sometimes things go down in a big way, and then the on-callers are very empowered to engage other people on the team to come in and fix whatever is broken in the infrastructure, whatever thing got overloaded, whatever thing fell down. And the reason that this is such an important role and why it's worth making a couple people's, work fairly annoying for a short period of time is because when there are system-wide issues, when there are too many failing tests, that becomes a significant negative impact across the project, and it slows everyone's work down. So this is a necessary role that helps everyone reduce the amount of toil that they individually have to deal with. And we do rotate this. We make sure it's not always falling on the same people. That's not fair, but it's also more important than that. It's important that everyone get experience with dealing with these breakages, because it makes you think twice before you throw that random commit over the wall. Another big process that we follow is this way in which we take a piece of IP from concept to actual tape out readiness, where we take it from, hey, that's a cool design and a cool implementation, to, all right, I'm willing to drop 7 figures to make that show up in reality. So we break it down into design, verification, and software sort of tracks. And then there's this meta track of the actual lifecycle stages. The called D, V, and S. These tracks are transitions between them are signed off by committers, just like everything else. There is a review meeting scheduled when someone thinks something is ready for transition, and then feedback's provided, feedback is addressed, device moves from one stage to the next. These are not linear stages. To go from V1 to V2, V2 complete, you have to have 90% functional coverage, 90% code coverage. So these are big, they can be big jumps. And when you get all three, like say you get to D2, V2, and S2, then you can talk about starting to move through a life cycle stage. Actually, I guess it would be D2 to D3 across the board. So when things are at the kind of sign-off stage, the tape out readiness sign-off, it's basically like incrementing like an epoch number, something along those lines. That actually goes through the technical committee so that it gets a broader visibility, so that we all kind of agree, yes, we'd be comfortable taping this out, ideally in a production design. So it's not just, challenges and stuff we did to fix them. It's not just, individual IP blocks or the design that we've developed. There are opportunities unique to doing this design in the open. Drawbacks, yes, it takes longer, but also some really significant advantages. It's not just about these challenges that keep me and my team employed, as much as we enjoy that facet. It is about enabling an open ecosystem, not just a single device. It's about serving as a platform for research, but also for commercial innovation and impact. It's about having a place to concentrate what is very specialized skills on a single design, and really bring that one design to the absolute peak of security. It's hard enough to get it right once. We are not sure that it's a great idea to be trying to get it right multiple times. And then this kind of foundational thing, which is really reducing the leap of faith we have to take for some of our most foundational security guarantees. Whether people realize it or not, they're carrying around probably 6 or 7 roots of trust, depending on how many credit cards you have in your wallet at any given time. I've heard of some phones have up to 3, 4 secure elements. I mean, these things are absolutely everywhere. So first thing is about enabling an ecosystem. We have a concept we call comportability that all IP has to adhere to. And what comportability is how we really make our blocks interoperate smoothly with each other, and also how we maintain a consistent and correct accounting between the device, the block description, and the documentation that the software engineers use to actually interface with it. So that's all programmatically generated from a configuration file. Learn from past experience. This is something we put a lot of work in early on, because it's really hard to get this right after the fact. And the last thing you want to do is be chasing differences between what you wrote in the documentation and what you actually implemented in the system Verilog. That leads to uncomfortable conversations. One interesting thing about this comportability and this strong enablement of reuse is that when we started the integrated root of trust working group, we kind of went through, looked at the architectures, did an inventory, and what it really looks like is we're basically 60, 70, I'd say 70, 75% of the way from the discrete design to having a integrated design complete. Big difference, obviously, is a lack of non-volatile, no E-flash in the really, really small nodes, but they're pretty canonical ways of solving that problem. All right, so another cool thing, and this is something that I had predicted would happen, or maybe I should say I'd hoped would happen, and I said it, and I was really, really happy to see when it did happen. But the notion that if we go and we build a kind of cohesive, high quality platform, unquestionably, commercial quality, then other people will leverage that to do research on top of, to build on top of, because it's out there, it's open, why not? Hilariously, the first time this happened without any coordination from us is I got an email from Christoph Parr out of the blue, who was like, oh, I took your design and I ran all this stuff on it and I'm publishing it. And I was like, well, that's kind of wish you'd reached out. We could have helped, like we would have happily helped. But there have been a number of people who have gone and done this and then kind of reached out after the fact. So the fact that it's kind of bubbling up from the bottom like that tells me that this is fairly successful. And I hope this doesn't count as an advertisement, but one of the papers here is actually being presented, I think tomorrow, SynFi, by, I believe, Pascal is probably presenting that. So it's not just prior stuff, it's happening like right now. People are leveraging this design, they're building on top of it. They're doing cool stuff with it today and publishing the results. Another cool thing, it's not just research impact, it's commercial impact as well. Nuvoton, obviously, they're building our first chip. We're working closely with them. They're using the entire design to make this commercially available secure element. But also, a couple of weeks ago, we found out that Microsoft had taken OpenTitan's IBEX processor and extended it with cherry-style tags. Now, that is something that I had really wanted to do for a long time, but resources are limited. And turns out, if you make it open enough and high quality enough, and you wait long enough, someone else will get to it for you. So I'm really looking forward to seeing that get upstreamed as a IBEX variant. So that'll be something fun to play with. Another interesting thing is this open platform. We were able to work really closely with Colin and Hillary at New AE and leverage a lot of their work to basically it's our development infrastructure, it's our emulation platform, it's our side channel analysis platform. The only constraint I put on them is that Colin has to keep naming these boards after his dogs. It's very, very important to me. So I think he's going to have to start getting more dogs now, but we'll see how that works out. But what was nice is that gave us something where we were able to work really closely with them and really understand the kind of value that they brought to this whole secure silicon ecosystem. And then that ended up culminating in low risk actually purchasing New AE, and we're now working even closer together, which is fantastic. So I'm going to close now on a final note, and I will acknowledge or say, you might reasonably ask, and I have been asked both of these questions a number of times, 2 questions about this project. Why are we doing this? And to what end? How do we want to see the world change as a result? So why? Few reasons. One, it's there, it's challenging, we can. It's also very motivating to be told all of that will never work. It's like, well, you sure? Because we made it work. Second, it's the right thing to do. It's great if people trust the design. They really shouldn't have to. This type of security is not a differentiator. It should be an expectation. And open source solutions are fundamentally more palatable to users, to partners, than anything proprietary can ever really be. And then one final reason why is, it's my belief, it's the belief of some other folks, that this domain, these kind of specialized domains like silicon security, and I've had more than one very competent cryptographer tell me they would really rather just focus on one library. They are very specialized. The pool is relatively limited that we're pulling from. There is probably in this room a significant double-digit percentage of people who are experts in silicon security of the world. That's a little concerning, but that is what it is. And so, there's this notion that it's hard enough to get this right once. It's not clear that we really move security forward by splitting our effort and doing it in more than one place. Okay, so next reasonable question. To what end? How is the world going to change? How would we want to see the world change as a result of this when it's successful? And I'm going to define success because it is silicon. It's not successful until you have silicon in hand. So I'm going to define success as silicon, commercially relevant silicon in hand, incontrovertible proof that open silicon can be successful. So I'm also going to say we're real close, months, not years. And I've got a very talented, committed team and partners that say we're going to get there. It's actually flying back from meeting our partners in Israel is why I had to stay overnight in Munich last night. So they're psyched, and it was worth it in the end. So here's my kind of spicy closing statement. Once this is successful, the question will not be why should we use open silicon? It's going to be why aren't you using open silicon, especially for something as critical to all of our security, like the silicon root of trust, these ubiquitous little secure devices that are everywhere today. So with that, thank you all for having me. Went a little bit over, apologize, but I am happy to take questions now and for the rest of the conference.
Thank you, Dom. Yeah, other questions? We already see some.
How OpenTitan is fitting into the current certification scheme?
Yes. Question was, how is OpenTitan fitting into the current certification schemes we have in security? I'm going to guess you mean common criteria. Nailed it. I'm actually giving a talk at some conference in Spain, and I think in like 2 months, where I'm going to cover all of that in detail. But it is a requirement that OpenTitan designed blocks be compatible with both FIPS and common criteria PP84, but also now PP117 for the integrated designs. It is not trivial to do that. We do have, we've had a security target for like 3 years now. It's quite extensive. So we've got both the technical collateral to do it, as well as the organizational collateral to do it. We have been engaged with more than one lab from the start. We also work closely with folks. I mean, G&D was our first partner. They do seem to know what they're doing quite well. And it's something that, while there's this like canard that you can't certify an open design, it's not exactly true. We have asked about this and gotten some quite a bit of feedback on it. I wouldn't say it's easy to certify an open design. And what it actually ends up doing is it ends up pushing the implementation, the security of the implementation that we have to do up a fair amount, because lots of belts, lots of suspenders, which leads to some very testy conversations with the partners who really just want to reduce area. But the thing is we have to overbuild it for the first time, evaluate it, build the lab, right? Or sorry, evaluate it in the lab, both our own and other external labs, so we can see where, if we can cut, we can cut, right? So it's foundational. It's something we consider from the very, very beginning. So, and you know what? It might fail the first time, won't fail a second time. So, yep.
Are there further questions? Actually, maybe you first.
is, it's a really somewhere.
Okay, so I'm sorry, I'm having a little trouble hearing. So I think I heard two questions. One was, how do we enforce that the stuff that has to be open source is open source? And the second one was, are hardware Trojans part of our threat model? Am I close? Okay. How do we enforce that something that must be open source is open source? It's going to be really obvious if they change it, because it's going to change what comes out of the key derivation engine, but also by contract. We have a trademark. You don't get the trademark if you could look, to be clear, this is a permissively licensed open source design. You can take it, you do whatever you want to it, right? You then cannot also necessarily call it OpenTitan. That's not okay, right? That trademark is pretty strictly controlled, and there is going to be an evaluation. Right now, the evaluation process is, well, we're only working with one backend vendor, right? We're only building one of these devices. We know very well what's going into that device. In the future, it will scale in a different way. But really, we will be irritated if someone abuses the trademark, and there are actual teeth on that. The second one, I don't want to say hardware Trojans are not part of the threat model, but we are certainly not claiming that we are solving that problem. Although it's my belief that we are doing better. We will do better tomorrow with that problem, with this design, than we have done in the past, because if you have a priori knowledge of the full design, you at least have a chance through, I don't know, metrology, reverse engineering, whatever, of being able to validate that what came out of the fab is what you put into the fab. But I would never claim that, like, can't solve hardware Trojans. That's good luck. Ask for money from the government.
Sorry, yeah, I think we start over there and take you after that, and then it's your turn. And
Okay, so that was about what, and I'd ask people to, like, I know my ears stick out, but it's less functional than you might think. So I'm having a little bit of trouble hearing folks. So just speak up, please. So I think what I heard was, what is our, how do we handle vulnerability disclosures? Yeah, so there is a vulnerability disclosure process, which my right hand, Miguel, who I'm looking in his general direction, assures me has been documented, and we will be reviewing it shortly. But basically, we're adhering at a minimum to the vulnerability disclosure requirements that the appropriate CC mandates. So we're at least doing that well. And then I suspect it'll, because of the cycle times of silicon, it won't be 3 months, it'll be 6 months or something. So there'll be some variation there. But yes, it is something that we have started working on, or that we have a draft of, and then it's starting to go through a review process. Oh no, I see you. Anyway, so yeah, we're well aware that that's an issue.
thank you. So please.
The point of regulation is how the individuals realistically back to the one part. Where now these are the change. So one of the more modern design. Where they can complications and also explaining to the attendant who's that the important way of my this is responsibility. We are the power, how do we step
So if I hear you correctly, you're asking, how do we handle the different process nodes, different applications actually require different configurations of roots of trust. They can be a little different, they can be a lot different. How do we actually handle that, right? Yeah. So I alluded to a little bit this thing called multi-top, where we're actually handling multiple top-level configurations and keeping that code base consistent in green. We've put a bunch of work into repo engineering to get this done. This is about it's going for discussion at one of the main working groups relatively soon. Now it's actually the integrated working group is basically forcing us to address this problem in a scalable way. What our goal is to have, we call them complexes, probably should have called them configurations, but you know, I made my bed, so I'm going to lie in it. So we call them complexes. Multiple admissible architectures, but a finite number, right? We don't want this to grow without bound. Although again, this is a permissively licensed open source project. If you were like, you know what, your big num engine, it just doesn't work for me, or your boot ROM, we don't like it. It's fine. You can change it. You can implement it. Just don't call it OpenTitan, right? It's absolutely fine, because the thing is that for us, you know, for a lot of the partners, the reason why they support this project is that fundamental transparency guarantee, right? The ability to get a roughly equivalent, you know, modulo some important things, level of transparency from a design as if they had made it themselves, right? So it can't grow without bound. There should be kind of baseline admissible architectures for a number of different points. And that's something that's under development like right now. But to be clear, our focus today is not on, we've already got our customers, we've already got our tape out partner, like we got a mission, right? So we're executing on that mission, and then we're going to keep working on the scaling of that to more and more designs over time.
Thank you. Yeah, sorry, I think we'll close the question session now. The last question we'll take offline, if that's okay, because we want to continue at some point. So thank you very much again for giving us these insights and for coming over.
Happy to do it.
So we have a track switch break now. That's a really difficult word to say if you say it like track switch break. Okay, so it's supposed to be 10 minutes. If you can make it in 7 minutes would be great. Thank you.
Very nice talk.
Thanks, appreciate it.
3 minutes is better. I'm going to stop.
No.
No? Okay. When are you presenting?